Lab01 presentation by me, Rhiannon Crisanti. This lab is a lab about the motion of objects, especially velocity over a period of time, where during a small period of time we expect a tracked velocity and predicted velocity to be similar, but over a longer period of time for them to be different due to forces acting on them that we don't consider. To track this hypothesis, we will be using a video of a tracked object moving and our fundamental principles with a velocity initial function so that we can put something into our predicted algorithm, a final velocity and a final position formula to actually predict that motion, and a velocity average function just to double check that the initial velocity makes sense. And here is our video. For a system, the duct tape is rolling down the surroundings, the table, with the background of a meter stick to help calibrate our tracker software, with these little blue dots being the actual tracking of the duct tape rolling down the table. And here's that data modeled through charts and these two graphs, where this one shows that our x values are in a negative direction and our y values are practically negligible due to its extremely small size. And we use this to find the initial condition, which is through this formula, where we take these first 2 points and first 2 times to plug in so that we can use it in our initial velocity again. And when you input the data from before, we can get not only the initial velocity vector but also the initial position vector. Here is our delta t, the time intervals we are going to be considering, and our force vector, which the magnitude is 0 due to Newton's first law saying an object in motion will remain in that motion unless a force is acting upon it, and because we are assuming that the motion will remain constant, there cannot be a force. And down here we have our final velocity vector, an equation which is the vector is being updated from adding our initial vector velocity to the force times the elapsed time divided by the mass of the ball, which will go to 0 due to the 0 magnitude force. And we will also have the position of the ball being updated the same as down here, with the initial position, the velocity times the time, and this part was not included in the coding, but that will go to 0, and it is the force times delta t squared divided by the mass. So these are there so that the velocity and positions are being constantly updated so that the model can be as accurate as possible, especially over small delta t's, that is being constantly shifted in the best way to create a smooth and accurate graph. Is it possible to say how many pushes and pulls are added together to give a 0 net force in the case that is observed? Whatever force caused the initial motion must be able to counteract a friction force, for example, that will be acting due to the table and the duct tape interacting. And for the magnitude of net t equals 0, that means that these two forces will need to cancel each other out and therefore be of the same magnitude but in different directions. Here's the charted data with it going in the negative x direction and the model going from here to here. And here's that those two points put into a chart side by side. However, the next slide will be most important. And this is the actual chart of these two motions, where the track points and predicted points are very similar here, but as time elapses, we can see a difference with the track points and the predicted points. And this error in our calculations is caused by not assuming there are any forces on the duct tape, which in a real life scenario there would be friction, air drag, gravity, all those forces that would actually be acting upon that we don't take into account. So that accounts for the difference in error. And if the movement was in the opposite direction, these values would really just be positive instead of negative. Thank you for listening.